It's Professor Dave. Let's discuss L'Hopital's Rule.
He knows a lot about all kinds of stuff. Professor Dave explains.
Over the past few tutorials, we've learned all about differentiation and its applications. With differential calculus more or less wrapped up, it is just about time to move on to integral calculus. But before that, let's revisit limits for a moment. When examining these, we saw that we ran into problems when trying to evaluate limits for functions where both the numerator and denominator approached zero. This limit is indeterminate, meaning we just don't know what it's doing. 0 over anything is 0, but anything over 0 is undefined, so we just can't interpret this result. Luckily, there is a rule we can apply in such a case. This is called L'Hopital's Rule. This rule works as follows. Say we have some expression in the form of f of x over g of x, and we are interested in the limit as x approaches some value a. If both of these functions are differentiable, and both of them approach 0 as x approaches a, this indeterminate form can be evaluated if we take the derivative of each function. In other words, the limit of f of x over g of x as x approaches a is equal to the limit of f prime of x over g prime of x as x approaches a. Let's apply this to one of the functions we looked at when we first learned about limits. If we look at sine of x over x, and we want to know what happens as x approaches 0, it seems impossible, as both sine of x and x approach 0 as x approaches 0. But using this rule, let's just take the derivative of the top and bottom. Sine x becomes cosine x, and x becomes 1. Now let's just find the limit of cosine x as x approaches 0. The cosine of 0 is 1, so this limit equals 1. We got this answer previously by plugging values into the function and seeing what happened as we got closer and closer to 1. But I think everyone would agree that using L'Hopital's rule got us to the answer much faster. Let's try a couple more for practice. How about the limit of e to the x over x cubed as x approaches infinity? Now this one doesn't give us 0 over 0. It gives us infinity over infinity, which is still an indeterminate form. So let's use L'Hopital's rule. Taking the derivative of the top, this will remain e to the x. Taking the derivative of the bottom, we get 3x squared. This is still infinity over infinity, unfortunately. But here's a great thing about this rule. Why not just take the derivative again? If the limit of the quotient of the functions is the same as the limit of the quotient of the derivatives, then this truth will hold, no matter how many times we take the derivative. We go again, and e to the x stays as it is again, while on the bottom we get 6x. This is still infinity over infinity, so let's go one more time. We get e to the x over 6, and finally we can see that this will simply be infinity. Remember, this rule only applies to limits of indeterminate form, so 0 over 0 or some kind of infinity over some kind of infinity. If either the numerator or denominator is not one of these, we can't use the rule, so always check for that first. For example, take something like x plus sine x over x plus cosine x. We could be tempted to use the rule, but we must note that while the numerator goes to 0, since sine of 0 is 0, the denominator actually goes to 1 because cosine of 0 is 1. That means 0 over 1, which is 0, and we did not have to use L'Hopital's rule to get there. In fact, if we were to use the rule here, we would actually get an incorrect answer, as we must have an indeterminate form for the rule to work. Lastly, let's look at some slightly different forms of the rule. Say we have an indeterminate product, or the limit of a product of functions where one goes to 0 and the other goes to positive or negative infinity. Again, we can't directly determine what is going on here. In such a case, we can rewrite fg as either f over 1 over g or g over 1 over f. Now we have a form for which we can apply the rule that we already know. For example, take x times the natural log of x as x approaches 0 from the positive direction. Naturally, x approaches 0, but the natural log of x will approach negative infinity. Well, let's write this as one function over the reciprocal of the other. How about natural log of x over 1 over x? Now we can take the derivatives. Natural log of x becomes 1 over x. And x to the negative 1 becomes negative x to the negative 2. Let's multiply the numerator by the reciprocal of the denominator, and we simply get negative x, so the limit must equal 0. We can do something similar with indeterminate differences. If the limit of a difference of functions gives infinity minus infinity, it is impossible to know which infinity wins, to give infinity or 0 as a result. But depending on the functions, we can do algebra to convert this into a quotient, whether by trigonometric identities or by getting a common denominator so that we can apply L'Hopital. Lastly, we can also have indeterminate powers. That's when a function is raised to the power of another function, and we end up with something difficult to interpret. This includes 0 to the 0, infinity to the 0, or 1 to the infinity. In such cases, we can set the expression equal to y and take the natural log of both sides, so that natural log of y equals natural log of this expression. This allows us to bring the exponent down here to the front. Then, so that we have just y instead of ln y, let's realize that by the definition of logs, y must equal e to the power of all this. When we take the limit of this, we may now be able to evaluate it. For example, how about x to the x power as x approaches 0 from the positive direction? This would give us 0 to the 0, which is no good. But if we do the steps outlined a moment ago, we end up with e raised to the power of the quantity x times natural log of x. In the previous example, we showed that x times the natural log of x goes to 0 as x approaches 0 from the positive direction. So this limit becomes e to the 0, which is 1. So with that, we now understand L'Hopital's rule, and we have come full circle with limits and differentiation. We are now truly ready to move on to the other side of the calculus coin, which is integration. But first, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.